So to recap what we did last day, we went through very briefly Planck's equation, which is our base equation for our brand new field of quantum theory. And I just lost my pen again. Yeah. All right. Really, really quick equation, quantum theory, where E is equal to hf. And here's where he had looked at the possibility of energy existing in quantas or packets of energy, which is very, very different to what they had assumed from years before. All right, where we thought that energy was a consistent flow from a object or system. All right, he proposed something very different. Why did he propose this very different idea and concept? Because we already just established that charge exists in packets. All right, as in electrons have multiples of charge. They don't have half values, three-quarter values, is either 1 or 2. So that means they existed in pulses of an exact value. So they probably went with the same kind of idea, right, at the time to see what they'll get. Why did I lose my pen? All right, let me just pause. So we're going to continue today with quantum theory. All right, continue with quantum theory. So that's reading. We can zoom in a wee bit more. All right, so we're going to touch on what we finished up with last day. When Planck released his findings, I decided further derivations that properly describe the photoelectric effect. Remember, this is what I told you Einstein won his Nobel Prize for, right? It was not for relativity. It was for his work with Max Planck regarding the photoelectric effects. If you all want, go and read it up, what they actually did and whatnot. He assumes that not only will light and other forms of electromagnetic radiation emitted in quantas, but will call photons. So those little packets of energy, those little pulses of energy are called photons of energy. So continue reading. This is where we're going to do the maths today. When dealing with thermionic emission, now thermionic emission is another name. You all are going to see this in exams. That's why I give you as many names as possible for your terms. Is another name for the photoelectric effect. All right, so thermionic emission means similarly, that's what we call the effect, the emission of those photoelectrons is the thermionic emission. So reading. When dealing with thermionic emission, the amount of energy required to liberate an electron from the surface of a metal is called the work function phi. So work function phi is the amount of energy required to liberate an electron, not just a regular electron, a photoelectron. Why do we call those photoelectrons again? Anybody want to tell me why we call them photoelectrons?
Look, Andy, mic blinking. Look now, baby.
This is because the photons come in contact with the electrons? No.
Kinda. Why they call them photoelectrons? Because they are these are electrons that are liberated with the application of light. Remember, I'm saying light in inverted commas, meaning that they are emitted with the application of electromagnetic radiation. Usually, we look at infrared, visible light, UV. Remember, we call all of those light. We have infrared light, we have visible light, we have UV light. Right? So that's why we call them photoelectrons, because they get the energy from photons and or they are liberated by using a light. All right, so continue reading. Work function phi is characteristic to each metal. So remember, we always have something called characteristic properties, as in they're used to define that metal. They're used to define that gas, that material, like density is a characteristic property, specific capacity, refractive index if it's transparent. These are all what we call, and we use them to describe and identify materials by their characteristic properties. So remember, this can go way back to Archimedes, where they determined that density is a characteristic property of a material. And by finding density, we could determine what the material is. Here, work function is also a characteristic property. So we use it to determine what kind of metal we have. We can determine whether or not your metal is pure, whether or not you have alloys, just by looking at the work functions. Amazing how many things we have to define materials around us. So it's not like, you think it's metal, I think it's zinc. No, there are tons of experiments, tons of data out there to define your materials. So continue reading. Einstein proposed that a photon of energy HF, remember HFE is equal to HF, causes an electron to be emitted if HF is more than the work function. So let's read this again. All right, without all of our colors on the screen. What is work function? First things first. Phi is the energy required to liberate a photoelectron, from the surface of a metal is phi. All right, and Einstein proposed that a photon of energy, so if this is our metal, like what we did last day, and we shine a light, remember light here means any sort of electromagnetic radiation of energy E is equal to HF. Remember last day we said it must be of a specific frequency to have the right amount of energy, because energy and frequency are directly related to each other, as we see in this equation. So only if the amount of energy that is hitting my metal, only if HF is more than the amount of energy required to liberate your electrons, will the photoelectric effect happen, which makes sense. If it takes me 5 joules of energy to liberate an electron and I am supplying 4.8 joules, nothing is going to happen. All right, you need to have a little bit more energy than what is required in order to ensure that this liberation of that electron happens. This is our first set of relationships that we have, right? Where HF must be greater than your work function phi in order for the photoelectric effect to happen. The excess kinetic energy, being whatever is left over, appears as kinetic energy. And what is this kinetic energy used to do? It's used to cause your photoelectron to move. So let's look at how the maths plays into here. Really simple maths. At our level, we can understand this is nothing maths now. Amazing how far we reach in our mathematics, guys? Right? When we can say this is nothing maths. Let's think about this. If I have a wave of energy E is equal to HF, and it hits a metal that has a work function of phi, right? And phi is the amount of energy it takes to kick out that electron. The excess energy, so suppose HF has to be greater than phi. If it's equal to phi, you're just going to get a little bit of the electrons getting liberated, but just liberated. So that means they will not have enough energy to move away. And we know, as far as we know, electrons have a velocity. Don't electrons have a velocity? They have 2 types of velocities. You all know that, should know that. Silence in my class, boy. All right. Remember, we have electrons that are accelerated by an electric field. That is what travels nearly at the speed of light. And then we have electrons, well, when it's in a metal, that have a drift velocity. It's much, much slower, but it still has energy to move. Likewise here, if I use something as energetic as electromagnetic radiation, where my frequency is 10 to the 14 hertz. That's a lot of energy regardless of the value of Planck's constant. So if I have a lot of energy being pumped into my metal, obviously those electrons are going to fly out and they're going to have a particularly large velocity. So let's look at this again. If I have a wave of energy E is equal to hf and it hits a metal of work function phi, this electron will only be emitted if your energy is greater than your work function. Emitted being it's accelerated outwards from the material. And if this is an energy value and this is the energy value, right? One is the applied energy. This is your applied energy to your metal. This is the energy required to liberate your electron. Then the excess energy will be used to accelerate my electron. So let's see, right? Using the maths, right? These are both forms of energy, right? So that means HF minus phi will be equal to half mv squared, where half mv squared is the kinetic energy of my electron. And electrons have a mass? Electrons have a mass. You all could give thumbs up, tick yes, or do something as response. You don't just have to always say yes, miss. Right? The electron, right? The electron will have a mass and it has energy, and this energy is kinetic energy. We know that kinetic energy is half mv squared. Electrons have a mass, it will have a velocity, so we can read its kinetic energy. So let's read what we have else on the screen. But we also know that, whoopsie, that HF cannot exist below phi. So there could be a point when they are equal. There could be a point when they are equal, and what happens, your electrons will not move. They will be liberated, but it'll just sit down there. All right, so the above equation, let's look and see. All right, we have E is equal to HF. All right, that's our first equation. When we have phi is equal to HF, let us rename that frequency as F naught. So F naught is the lowest possible frequency needed to liberate that electron. So we just put in everything here in forms of energy because energy is equal to HF and phi is also an energy, all right, of a material, of a particle. So we can put it in here. If phi is equal to HF, then HF minus phi will give us HF, not equal thing, HF minus HF naught, where F naught is the lowest possible frequency possible that my liberated electron will have, or the minimum amount of energy needed to liberate that electron, that photoelectron. So what we can do here, we can factorize out Planck's constant. So H is equal to F minus F naught is equal to half mv squared max. We call this max because it's the maximum velocity that the electron will have at the time. How much energy we have left over from the interaction is the maximum amount of energy my electron will have. Of course, once it travels, it is going to lose energy as it moves. Well, unless in space, and then it has nothing to slow it down, it will continue moving at the same velocity. Please note, you all, this is velocity squared. They are not talking about acceleration. And this again tells us about the instantaneous event and effect that is the photoelectric effect. Remember we said, as we have our, where did it go? All right, if we have our metal and we shine that light onto that metal, immediately and a photoelectron is pushed out of the metal immediately. There is no sort of warming up where it absorbs the energy, it breaks a bond, and then it becomes liberated. It's almost as if it's just sitting down there waiting for the light to come and push it off. It's almost like that. So what happens? It gets kicked out with this velocity. It's not like, it accelerates from rest and it gradually increases in speed. This is why we said that quantum physics is something very, very different. It basically violates Newtonian physics or classical physics because we didn't know about it as yet, because we didn't know that electrons contain so much energy in them. We didn't realize that there was so much energy contained within an atom to the point where it stores so much energy, it just has instantaneous motion because it already has that energy. It doesn't have to absorb any energy, if you can understand what I'm saying, right? All of these things have energy already, so they don't have to absorb it and break a bond. It already has the energy ready to go. Right, so that's our first equation. That's equation 1. Okay, I don't know why it disappeared, but all right. All right, so equation 1, H is equal to F minus F naught, where F naught is your work function frequency. That's the very, very lowest frequency needed to liberate your photoelectron. F here is the applied frequency, so that is the energy of the electromagnetic radiation that's coming in to hit your metal. And half mv squared is going to be the energy of the photoelectron that is emitted. So look at that, we have incoming, hits our surface, and we have outgoing. We have 3 players in that story, and they all play into this equation. Incoming radiation, radiation required to have liberation, and accelerated, well, not accelerated, but moving electron. Stopping potential. All right, stopping potential. Why are you doing that? At a particular value of voltage, which is V subscript S, the current becomes 0, meaning the current required to cause this photoelectrons from being emitted becomes 0. This PD just stops the electron from moving and is called the stopping potential. Since this will stop the electron, it will have the same energy. So what is stopping potential? This is if you take your photoelectron in a glass tube or in a electric field, and you have 0 and you have Vs, we can cause that electron to stop moving. Just as we did in Millikan's oil drop experiment, we can cause a charge to stop moving. Here's the same thing. So there's a particular voltage you can apply if you have your photoelectrons within an electric field. If we have a particular voltage being applied, we can stop those photoelectrons from moving and just keep them stationary. So here we can have, remember we had done before, energy is equal to EV. All right, this is our next way of recording energy of very, very small particles, of charged, very small particles. We use electron volts because half mv squared mgh for something that's really, really, really tiny makes no sense. All right, here we use the energy contained by an electron. All right, so here it's going to be 1.6 by 10 to the minus 19 by our voltage. So here we're going to have the maximum energy in your system is going to be equal to your E by V, because we know energy is equal to charge of the electron by your voltage, and V is equal to the stopping potential, meaning it stops everything from moving. So now you're going to have it equal. If all your values are equal, you're going to get a sum of 0. So you're going to have EVS will be equal to HF minus phi. Please note you can always go and rewrite this equation now. You can expand this equation because we're going to use it down in energy levels to give us EVS, which is charge of electron by stopping potential, is equal to H into, why am I drawing out? That's because my finger hurts. H into F minus F naught. So this is another way of writing this equation. And then we could expand this even further. And we could have half mv squared. So look, we can use this relationship here, put all our equations together, and we could use the charge of an electron and the voltage of that electron to work out the velocity of that electron. You all see how we can do that? Just by taking out, let's take out this relationship in the mean here. We can have all of these equal to each other. All right, so this is why we have sequences of equations that can help us work out our motion of our photoelectrons and whatnot. So if you all want to write that in, you write it in. I hope you have your handouts printed. Honestly, guys, you should have it by now. So these equations are going to come in very, very handy. You see this sequence of equations come in very, very handy when we have to look at the amount of energy contained by a photoelectron, the velocity of your photoelectron, the amount of energy required to cause photoelectric effect to occur. All right, we'll see these in questions when we finish this handout. All right, so we're going on to energy levels. Physicist Neil Bohr, of course, all the guys we talk about here. Yes, all the guys and one gal. All right, all the guys we talk about here do have Nobel Prizes in physics. Of course they did, right? Because they helped set the stage for what we're doing now. Sorry. So physicist Neil Bohr proposed that an atom has a number of separate energy levels or energy values or levels. These levels are characteristic of each atom. So this means that every element has its own energy level diagram. Chemistry students, have you all ever done these energy levels? You should have by now. Yes. All right, so this is where the two topics do cross, because I do remember doing this in the GCE levels. I didn't do CAPE, remember, I was before CAPE. All right, so these are where our two topics overlap. All right, so what we have here, every single atom has a particular amount of energy, but even more specific, every single element has their own specific energy level diagram, meaning there's a certain amount of energy for each level of your electrons and whatnot. All right, and that is how we're able to determine the amount of energy in an atom by how much energy your electrons have. So continue reading. The levels can be represented by horizontal lines arranged one above the other to form a ladder. Remember we did this, something similar to this when we were doing semiconductors, where we had an energy level diagram, where we had a whole bunch of energy in your valence band, and then you had a large gap or small gap, depending on your material, a large gap to go up to your conduction band. Remember we did that? It's the same exact thing, except for a different point here. So we did that. Remember, we had done that in module 2, where we looked at your valence band, and then we had your conduction band, and then we could introduce holes and free electrons. Remember doing that? Sort of. Okay, or let's start revising it. All right, it's the same energy levels diagrams that we're using, except to a different point. So continue reading. As electrons moved from one level to another, something's missing that sentence. Where are they? As electrons move from one level to another, while it is permitted to move up and down, it cannot exist between two levels. This is coming from our whole concept of quantized energy values. You can either have energy value A, energy value B, but not in between. Comes from the same thing as quantized charges. You can either have 1.6 or 3.2, right? By 10 to the minus 19 coulombs for an electron. You can't have in between. Same thing here happens with energy levels in a material. You could either be at band 1 or band 2. You cannot be in between. You don't have electrons that have a whole range of energies. Why? Because energy levels are quantized. Remember, quantize means to exist in levels or multiples of a fundamental value. An atom can then, not this, can then only accept parcels of energy, meaning exact numbers that will make it jump from one level to another. Right? If you do not have the exact amount of energy for your electron to go from one level to the other, guess what? That energy gets emitted. It's not enough. You know, it's kind of like going to the parlor and you only have 50 cents, so you want to buy something for 75 cents. The man go tell you just go your way. You don't have enough energy or enough money. Same thing. All right, so this is where we say energy is quantized, exists in packets of energy. Packets of energy being little pulses of energy. All levels have negative energy values because the energy of an electron at rest outside of an atom is taken as 0. And when the electron falls into an atom, energy is lost as electromagnetic radiation. So let's just see what that means. If I have, well, we'll see it in the diagram just now. The most stable state is ground state. Each element has different ground state values, and this is usually the lowest energy state available. Once above this, the atom is said to be excited. An excited atom is simply any atom, any electron that has more than the ground state energy level. Once you go above that energy level or that energy ladder or that energy line, you have an excited atom. This atom now has more than the normal set of energy, and it's probably is going to start emitting energy in some form or fashion. Because remember, the very basis and foundation of the universe is everything wants to occupy the lowest energy state possible. And what it does, they emit energy in the hope of reaching that lowest energy state possible. Everything doesn't have the same lowest energy state, but every single thing around us is a result of excess energy being emitted. Think about that for a second. The only way we see light is because an electron is now losing energy in the visible spectrum. The only way we feel heat is because something is giving off excess energy in the infrared line. The only way we hear things because excess energy now vibrates the molecules through the air and then through your ears into the bones in your ears. So that's, if you want to go down very, very simply, we experience every single thing around us because of excess energy. If we did not have any energy at all in anything, nothing would exist as they will, as they are, because we would be at 0 K, right? No electrons would vibrate, no sound would move, no blood would move, nothing will exist in a moving fashion. So let's look at our energy level diagram. So this is how our energy level diagram exists at. We call our levels N levels. So we have N level 1. N level 1 is known as ground state, right? So ground state is the lowest possible energy that your electron can have. And why do we call these negative numbers? If we have an electron, a dog just came inside, sorry. Right. So if we have an electron, a free electron, that free electron has a lot of energy in it. And in order for that free electron to get absorbed into an atom or to fall into an atom, that's why we call it falling into the atom, because it has to go from outside of the atom and fall into the atom. All right, that's basically what it is. A free electron falls into an atom, and the only way it's going to fall into an atom, let's use the wrongest possible analogy right now. If this is ground and something is falling down, isn't it losing potential energy? Anybody? And when something falls to the ground, it loses potential energy. Yeah, right? Because remember, potential energy is defined by how far you are away from ground. Likewise, using that analogy, the more, the further away an electron is away from the atom, or the further it is away from the nucleus, it has a lot of energy, right? Because it's now a free electron, and now for it to fall back down into your electron, to fall back down into your atom, it has to lose some energy. And the how do we calculate lose or loss? It's a negative number. Loss is a negative value, right? Anytime we decrease something, we are making it negative. So this is why the energy levels in an atom are counted as negative values, because your electron has to lose energy in order for it to fall towards the nucleus. Right? So it's a brand new concept, but as long as you're falling towards your nucleus, you have to give up energy, because you are now a free electron with a large amount of energy. And for it to go down to lower energy levels, you have to lose more and more energy for that to happen. So that's why our E's are in negative values, because we are losing it in order to form. There's no such thing as negative energy. We know this, right? Energy is energy. The negative value here simply means this is how much energy that the electron will give up. Give up means to lose, or it becomes a negative value, because that's how we mathematically deal with these numbers. So if you're wondering, but Miss, how you gonna have negative energy? No, the negative sign there is just mathematical to indicate that's being lost. Lost is subtraction. So let's read here. At 0, the element has now reached ionization level. This is 0, E is equal to 0. What is ionization level? Anybody? What happens when we've ionized an atom?
That will be the okay, it will be 0. No, okay, never mind.
What is ionization? Chemistry people.
Well, that is why you're breaking up atom into ions
And how do you get ions?
by supplying energy to break it.
How do you make an ion? In the simplest form possible. How do you make an ion? Either a cation or an ion. How do you make an ion? You make ions by moving electrons. We can either take an electron out of one atom and carry it to another, or we can take an electron and bring it towards one. So that means we must have a free electron. Ionization is where we create free electrons, right? That sounding familiar? Once we ionize the material, we have taken out an electron, or we've added an extra electron, and the only way we can do that is by ionization. Valence, covalent bonding is where we share electrons, but ionic bonding or ionization is where we take an electron and move it, where we have the action of free electrons. As I said, chemistry. All right, so at 0, 0 is here. This is n being infinite, infinity being it's out of the atom. A free electron is produced. So for hydrogen, this diagram we have here is for hydrogen. So for hydrogen, from minus 13.6 electron volts to 0, it requires 13.6 electron volts of energy to ionize one atom. For hydrogen, if N1 is equal to minus 13.6 electron volts, then the energy it's going to take to go from from minus 13.6 to 0 will be 13.6. Remember here, the negative sign is only an indication of loss. So you're going to have to lose energy, or you're going to require 13.6 electron volts to ionize one hydrogen atom. And we can convert this to joules. Remember to convert electron volts. Let me just clear up this board. It's a little too much. All right. Remember to convert electron volts to joules. All you have to do is multiply by 1.6 by 10 to the minus 19. That's all you have to do. So here, if I have 13.6 electron volts, that is the amount of energy it's going to take to go from energy level N1 straight to ionization level, which is N infinity or E0. All you have to do is take the difference between the two values. So 0 minus 13.6 is 13.6. Continuing, for more complex atoms, electrons are arranged in shells. All the energy states in which the electrons in one group can occupy about the same value. Each shell is given a principal quantum number n, and they're labeled in ascending order of energy levels of K, L, and M. So what happens? We have distinct energy levels, and we've named those distinct energy levels K, L, and M. There's more, but let's just look at the first three. So let's see what we have. Where do I have K, L, and M? Oh, it's not here. Okay. When an atom falls from the first energy level to ground level after it's excited, the radiation is emitted by working out my change in energy. So what happens? Suppose I have ground level. Why? All right, I have ground level, energy level, and this is my ionization level. So I have e to the 0. Suppose is e to the 1. Suppose my energy was somewhere, okay, I want to work out the amount of energy it's going to take for my electron to fall from E0 to E1. Remember, E0 here is the energy that it gets liberated at or becomes ionized at. The energy that's going to be liberated by my electron is simply going to be the change in energies from E0 to E1. All right, so if we look here, if you want to go and look to the question above or look to the state above, the amount of energy it's going to take for a hydrogen atom to get ionized or a hydrogen electron to get ionized, it goes from N1 to N infinity, or from E1 to E0. All right, and that's the amount of energy that will have to be given off in order for it to be liberated. Remember, excess energy here is manifested in the form of some sort of electromagnetic radiation. So let's read and see. When an atom falls from the first energy level E to ground level E0 after it's excited, the energy is emitted. The energy or the radiation emitted is given by the equation E1 minus E0, which is equal to HF, or C is equal to H by C over lambda. Where did we get C over lambda? Anybody want to make a guess where that came from?
From F.
How I get F? How I get that?
Well, F is equal to C over lambda.
How? Why?
That how it is?
No, that's not how it is. Anybody remember your fundamental wave equation?
F will be the frequency, right? And C is the speed of light over lambda. So it you know, it's
No, man. Very fundamental wave equation is V is equal to F lambda. Remember that? We all learned this in Form 4.
yeah.
Yeah? And anything traveling at the speed of light, being electromagnetic waves, all electromagnetic waves in a vacuum travel at the speed of light. So we're going to have C is equal to F lambda, where C is the speed of light. So if you want to go ahead and find different values of this, F will be equal to C over lambda. Likewise, if I wanted to find lambda, which is the wavelength of my light or my radiation, is equal to C over F. Make sure and write that down. That comes from your very, very fundamental wave equation. The first wave equation is V is equal to F lambda. All right, so that's how we end up getting this relationship. So the energy given off by your electron falling into an atom or by your electron getting liberated from the atom is the same amount of energy, right, going up or down. All right, so the energy when an electron falls into an atom, meaning it gets attracted or comes back into the atom, is going to give off that excess energy. And that excess energy, we can calculate that excess energy. All we have to do is see what our energy at one level was, see what the energy at the next level is, find the difference, and then we could work out the frequency of the radiation emitted. Remember, radiation here stands for anything along the electromagnetic spectrum. So that's from radio straight up to gamma. Radiation is not just radioactive emissions. You have to please get that in the head. All right, radiation is an indication that something is being radiated or usually some sort of electromagnetic wave. So continue reading the transitions from some of these lines in the visible spectrum of the electromagnetic spectrum of atomic hydrogen is called the Balmer series. The Lyman series is in UV rays and the Paschen series is in infrared. So the energy levels of an atom can be identified by color. How amazing is that? We can identify what level your atom is moving in, whether it goes from ground level to the first level, whether it goes from ground level to the third level of energy, or the third bond, the third shell of your atom, from ground to the third shell, just by the color of light that is given off. That is how we are able, of course I'm going to bring astronomy in now, that is how we are able to determine the type of gas that is in a star that is far away. That is how we are able to determine the type of gases in a gas cloud very far away, like in a nebula or whatnot. All we have to do, take the light, we analyze the frequency of the light. By looking at the frequency of the light, we are able to back calculate what is our change in energy levels. Chat. Yeah, red shifting and blue shifting, yep. Right, these actually comes from spectroscopy. If you look down here, Jabari, let's just go a wee bit down. You're going to realize if you had looked at your handout, we're going to look at diagrams that you remember from astronomy. All right, this is how we are able to identify what type of gases are in a star. This is how, just by looking at the type of gases in a star, we can determine the age of that star. We have bright people, you know. So imagine just by looking at a star and analyzing the light coming out from that star, we know how old it is, we know what type of gas it is, we know the concentration of each gas. Just amazing. I don't know if you all find that amazing, but I think that's wow. We can just look at light and determine so many things about something that's billions and billions of kilometers away. All right, so it comes simply from this. We just look at how the light changes in something that's given off electromagnetic waves or radiation, and we can determine what levels these electrons are falling. What do we mean by electrons falling? That they are above ground level, which is the lowest energy state possible, and when they fall, meaning they lose energy, they give off that excess energy in the form of a wave. We can record and measure the frequency of that wave. All right, now you're going to say, but miss, we could only see light. How are we seeing infrared and how are we seeing UV? Anybody? Yeah, let's think about that. Can we see infrared, as in we, humans?
No, not physically. No.
Nope. Can we see ultraviolet?
No.
No. But what we do have machines, we do have apparatus and devices that are able to record these different forms of radiation. And that's how we have infrared cameras that are able to pick up heat signatures. And we have UV lights and whatnot that are able to pick up different spectrums of light. So we do have devices, if it's not in optical range being visible light, we do have devices that record frequencies of light or electromagnetic radiation in the entire spectrum. Just to give you a little one, on Hubble telescope, we do have an infrared camera that records heat signatures. So we are able to record infrared light. We do have UV light recording. We do have a couple telescopes out in space that record X-rays, to record the X-rays given off by galaxies and black holes. All right, so we've learned to look at across the entire spectrum because we realize we can only see light. Bees and some insects can see ultraviolet. You all ever heard of that?
Yeah.
Biology people? No, they're able to see it because they have more sensitive light sensitive cones in their eyes that are able to record or identify a larger range of energies. Similarly, other insects record heat. That's how a mosquito could find you in the dead of night when it's pitch black. All right, that's how they find you, by infrared signatures. All right, so they look across the spectrum. We only look at visible. We are built to handle visible. That doesn't mean everything across the universe is built to handle visible. Thankfully, we've discovered insects and animals that look at both UV and infrared. I don't think they've found anything yet that does X-rays and gamma as yet. So let's look here. Anytime we have something emitting energy, so let's go back and see. All right, Balmer series is visible. So Balmer is visible. Lyman is UV. And Passion is infrared. Of these three forms of light, which one is the most energetic? Visible, ultraviolet, or infrared?
Will be UV?
It will be UV because UV is further down the electromagnetic spectrum than visible and infrared. And remember, we said the energy of a wave is defined by the equation. Why? Okay, then this way. E is equal to HF. The greater the frequency the light is, light being the electromagnetic wave, the greater the frequency, the greater the energy. And if you want to go, we have radio, we have microwave, we have infrared, we have Roy G. Biv, we have UV, we have X, and we have gamma. Radio waves are the very smallest frequencies. Gamma rays have the largest frequency. So this is how you're able to see which one has the most amount of, or the highest energy wave. Gamma rays are the most energetic wave that we know of so far. We haven't discovered the entire universe yet. There might be something greater, right? So we have X. So if you look at this here, UV has the greatest amount of energy, followed by visible, then infrared. Let us see why these happen. If you look here, Lyman series gives off ultraviolet light. And if you look here, anything that falls to the ground state, any sort of electron, excited electron that loses enough energy to fall into the ground state, meaning it gets fully absorbed back into the atom, it is going to give off enough energy to be in the UV range. UV range here being the most excited energy state, or most excited energy value of your waves. So anytime an electron gets pulled back into an atom, as an absorb back into your atom, it's going to give off enough energy to be in the ultraviolet range. Similarly, Balmer reaches n equal to, anytime it falls back to n equal to 1, you have Lyman. Anytime something falls back into n equal to 2 level, which is just above getting absorbed back into the atom, it is in the Balmer series. So it doesn't matter from which level it falls. Once it falls back to level 2, you are going to have visible light. And then if you fall back to level 3, you will always be within the Passion series, or you will give off heat. Now, this is how we are able to record heat. This is why things produce heat, because the electrons, the excited electrons, are falling back to a level, or they're gaining enough energy from level 3 to go to a next level. Right? When you burn something, you don't ionize it. Right? We don't turn things into ions when we burn something. If you all look at that, right? You ever thought about that? Why we don't, why isn't burning considered ionization? Yeah? Right? Ionization and burning is two very different things. Melting on something does not create ions. It creates steam. It creates gaseous particles. But an ion is not necessarily something that is gaseous. So it's a lot of twists and turns in the story of how energy levels work. So imagine we are able to melt something down and still not turn it into ions, because yes, we've broken the physical bonds of the material, but to say we have enough energy to go inside of the atom and take an electron out of your atom, no, it's not enough. Melting things is not enough energy to cause it to pull out electrons. That's a different energy level. That's a different process. So anytime something falls back to level 3 or goes from level 3 to outward, gives off infrared light, or it's in the infrared range. So you all have to remember which one lies in which. Right? Lyman, Balmer, Passion. If I were you personally, I would remember the order. Lyman, Balmer, Passion. Right? Being, we're going from biggest to smallest. LBP. Remember find some way to remember it, to see which level lies what. Now you do both, you get these in both paper 2 and paper 1 for your questions. So we will stop here. Next day we will do questions on it, even though I jump straight into spectra afterwards. We'll do a little bit of questions on them, so you will see where we reach. So remember I told you all I'm going to record a class because we only have one class this week, and that's really not enough for us to finish up. And I'm going to record this session probably later today. Now, spectra is a reading topic. Honestly, it is. It's not particularly any maths or anything, so I can very quickly go through spectra, right, and finish this up. So I'm going to record a session sometime this evening just to explain it out. As you see, there's no maths in this whatsoever. It's just explanation what spectra and spectrums are. So I record this evening, and I'll put it up probably sometime this afternoon, right, for you all to just peruse through. So that means next week we can go straight into X-rays and the rest of module 3. All right, so let me stop the share. So no, not stop the share, stop the recording.